So now we can start. So we will be discussing the following contents in the module. There are some more additional content which we will see. So first we start with an introduction as to what exactly are exoplanets and why do we actually want to discover them. And with this introduction, we move on to some early discoveries, some discuss some fascinating exoplanets which were discovered. Then we discuss what detection techniques were used to discover them. And then we discuss in detail all of these detection techniques, which are pulsar timing, direct imaging, gravitational microlensing, astrometry, transits, and radial velocity. But as for the content of the slides, we will be having a introduction as to what is an exoplanet and also the question why do we want to find them, and then we discuss what all parameters can be determined about these exoplanets. Then we will take a look at some of the fascinating exoplanets which have been discovered till now. Then we will take a look at NASA's exoplanet archive as to how they store the data on the exoplanets. And then we will finally see the detection techniques. We will be discussing two detection techniques, and it is just a brief, it's just an introduction. Those will be radial velocity and transits. You can, for more to understand better about the others, you'll have to refer to the module. We hope you do. So, without any further ado, let's start with the presentation. So, Ganesh will be providing the introduction. So, over to you, Ganesh.
Okay. So first of all, we'll start with a simple question. What is an exoplanet? An exoplanet is a planet that is found outside our solar system. An exoplanet may be orbiting a star or it can be a free-floating exoplanet. Such free-floating exoplanets are called rogue planets, and this planet orbit the galactic center in which they are present. Also, scientists study exoplanet to learn more about how planets are formed and to search for the signs of life beyond Earth. So there is another interesting question that why do we need to find them? When it's one reason is the curiosity of humans, and some more are mentioned down here. To find life beyond Earth, to find second Earth to live, to understand more about galaxy evolution, to explore improving environment that are beyond our current understanding. So here is a short video to explain what is exoplanet. Especially the screens and music.
Yeah, I'm just doing. Okay, one sec. So, is the video audible? It's not? Okay, one sec, one sec.
You've seen weird, wonderful worlds in science fiction. We don't yet know what sorts of life might exist out there, but some of the planets, not unlike the ones in your favorite stories, are real. At NASA, we're studying them. They're called exoplanets. The term exoplanet means a planet outside our solar system, a planet that doesn't orbit our sun. Most orbit other stars, but some are just sunless wanderers out in the space between the stars. Now, just the fact that they orbit other stars means exoplanets are extremely far away. Most are too far to even dream of sending space probes to explore them. So we study them in other ways, like with telescopes on the ground and in space that can observe these far off planets from right here in our solar system. Here's the thing about exoplanets, they are everywhere. In fact, from our observations so far, we know there are more planets than stars. So there's our solar system, then there are all the billions of planetary systems in our galaxy, the Milky Way. Then there are all the billions of other galaxies. Basically, there are a lot of exoplanets out there. Each of the stars you see in the night sky is the sun for any planets that orbit around it. But not all stars are created equal. Bigger stars burn way brighter and hotter and don't last as long. Smaller, fainter stars like our sun and red dwarf stars last much longer. But even nice, cool red dwarf stars can have powerful flares that blast their planets with radiation. We're still trying to understand which kinds of stars provide long lasting, stable conditions that could allow life a chance to take hold and evolve like it did here on Earth. Exoplanets are super hard to see, both because they're so far away and because they're so much fainter than their stars. But we've worked out some clever methods to detect them and even take pictures of some. So, what can we observe? Well, for many, we can determine their size, their mass, how much they weigh, and how far away from their stars they orbit. From these and a few other clues, we can infer a bunch of other qualities, like how hot or cold it might be on their surfaces, or if they even have surfaces. We can tell that some are gas giants like Jupiter, while others are like bigger, bulkier versions of Earth. For some, we can determine they have atmospheres and even some of the gases in those atmospheres. Most exoplanets are very different from our planet. They have a lot of weird, wild variety, with gas giants much bigger than our own Jupiter, and other planets with oceans of lava or rainy glass, or even gemstones. Funny thing is, looking at how they're arranged as families to planets, we don't see a lot of exoplanet systems that look like ours so far. Many are arranged quite differently, so we might actually be the weird ones. Some planets are closer to their stars, some are super far, some even orbit multiple stars. Imagine having two or three suns in the sky. So, why do we study exoplanets? Well, our interest in finding worlds with life on them is a big factor. We want to know more about what makes a planet a place with all the right ingredients and conditions for life, what scientists refer to as habitability. How does it happen? How common is it? We think the most life-worthy planets are the ones most similar to Earth, with a range of qualities that include similar size and composition to our planet, and being at the right distance from their stars to have liquid water on the surface. These qualities are really challenging to observe from so far away, but we're working on it. Exoplanets teach us a bunch of other things too. Studying other planetary systems helps us better understand the story of our own planet family, including Earth. Scientists detected the first exoplanets in the 1990s, but now we're finding tons more, thousands more. We're studying their atmospheres and even making weather maps for some. We're surveying exoplanets to understand all their variety. And the more we learn, the more it powers our curiosity, the more we want to explore exoplanets, planets outside our solar system.
Now let's move forward, knowing more about the exoplanets. So firstly, we'll talk about our limitation. I mean, obviously, we couldn't know each and every detail of this exoplanet at this stage of human knowledge, but in upcoming future we may. So who knows? So let's stick to what we know or what we can determine and try to understand. So here is a list of essential aspects about exoplanet that we can determine. The screen is
Okay, okay, one sec.
So here is a list that what all we can determine at our stage. That's the orbital parameter, which may include the orbital period or the inclination of the orbit of the exoplanet with respect to the line of sight of the observer on the Earth, the size and mass, the atmosphere, the habitability, and extraterrestrial life. So moving on.
So now let us take a look at some of the fascinating exoplanets which have been discovered till now. So first we have HD 1897773b. This exoplanet is interesting because it rains glass here, and but not just that, it rains glass sideways. Then we have Boswell B. It is a puffed up planet in the death spiral. Now, why is it a puffed up planet? Because it is because of its proximity to its star, which leads to if it being puffed up, and because of its proximity, the star it leads to strong tidal waves, which leads to the planet's orbital decay, leading it to a death spiral. Now that became a bit scary. Next, we have J1407b. This planet is fascinating because it has a beautiful ring system and a very massive one, which earns it the name of Super Saturn. Next, we can take a look at some of these exoplanets through NASA's Eyes on Exoplanets. Now, this is a 3D representation of how we think that these planets might look like. So, it is hypothetical, but you can understand more about these planets in general from these sites. The links have been added to the module, so you can also check it from there. So the very first one which we saw was HD 1897733b. So we can see a bit information about that planet here. Like it, like I already said, it is a giant planet where it rains glass. And how far away it is from Earth? It is 64 light years away. Then we have three different views over here. We have the planet view, then we can get its stars view, and also the stars information, or we can get the solar systems view, the planetary systems view. This we can compare it with our own solar system, and we can compare the planet with our own planet as well. It's quite interesting, isn't it? So, next planet which we saw was 12P. We can see its egg shape here. And now, if we view the solar system, its planetary system, we can see that it is very close to its star. And over here, there is also written that it is an egg shaped world which is being devoured by its star. So, like this, you can also check out other exoplanets and understand better about them. It's a really fun way of getting interested in this field. So, we hope you check it out. Next, we have is NASA's Exoplanet Archive. So, like the name suggests, it's an archive of all the exoplanets which have been discovered by NASA till now. So, as you can see here, we'll check a list of the confirmed planets. So over here, there is a lot of information about all the planets, exoplanets which have been discovered, along with their name, their star, the type, their star. It's a really good way to stay updated on the exoplanets, on their discovery. The internet seems to be a bit slow. Let's wait for just 2 to 3 seconds. If it doesn't come up, then we'll just move ahead. So we have the link to the NASA Exoplanet Archive in the module and also in the presentation. So if you would like to check it for yourself, then you can do so. We really suggest you do because it will be really helpful and also will get you interested. So let's move ahead. So now let's talk about how we detect these exoplanets. So let's talk about the detection techniques. So there are 7 basic methods used to detect exoplanets. So each of these are suited for different kinds of stars, and each of them come with limitations and advantages. So these methods are as follows. We have the Doppler method or the radial velocity method, transits, pulsar timing, direct imaging, gravitational microlensing, astrometry, and orbital brightness variation. The module discusses the first 6 methods, while in this presentation we will be talking about the first two, Doppler method, the radial velocity method, and transits. So starting with radial velocity method, over to you, Ganesh.
So screen chosen. uh, it's on.
Okay, give me 1 second. I'll figure it out. Really sorry, guys, but I think we can continue now.
So we'll start with the radial velocity method. So here is an example of an exoplanet HD189733b, which, if you may recall, Yashasvi have mentioned before. Its feature was that it rains glass on this planet that to sideways. This is an exoplanet which was confirmed using the radial velocity method of detection. So, so the next slide, please. So as we know that there is something important that we need to know in order to understand this method. That's the wobbling motion of a star whose exoplanet we are trying to detect. So what happens is actually when a planet's mass becomes significant as compared to the stars, it becomes more obvious that the planet and the star are orbiting together. They move together around the center of mass. And this motion is called wobbling motion of the star. So, so what actually happens is due to this motion, wobbling motion of the star, the frequencies received varies. So when the star is moving away from the observer, it is blue shifted, which we receive, and when the moving star, when the star is moving away from us, it is red shifted, which is also, if you may recall, called the Doppler effect. So, talking in brief, what how does the means radial velocity method works is that uh, the radial velocity method is like using a wobbler detector on a star. When a planet orbits a star, it pulls on a star just a little, causing the star to wobble slightly. By observing this wobble, the scientist can infer the presence of a planet. They do this by looking at the changes in the star's light spectrum specifically how the light shifts between red and blue as the star moves towards and away from us. This shift is similar to a way a siren sounds when sounds different as a vehicle passes by, called the Doppler effect. So the principle says that measuring the wobble of a star caused by a gravitational pull of an orbiting planet, this wobble causes Doppler shift in the star's spectral lines. One can think of radial velocity as the measuring the shift of the spectral line of absorption spectrum of star with time. We use a spectrograph to split the incoming light from the star into its constituent colors and measure the intensities using corresponding photo detector. So here is a short video that will explain what radial velocity actually is. It's also called the problem method.
Hey guys, how's it going? I'm in our next door, and today I was going to talk about how scientists detect extrasolar planets. So, an extrasolar planet is just a planet that is outside of our solar system. So, planets like Uranus and Mercury and Mars and Venus, those are not extrasolar planets. An extrasolar planet has to be going around another star. That's what we mean by extrasolar. So, there's actually quite a few different ways to detect extrasolar planets, but the big two is the transit method and the radial velocity method. So both these methods are indirect methods. What that means is we're not looking at planets and actually photographing them. So when astronomers find bodies inside the solar system, they like to directly image them. And what that means is they're just taking a picture of them. So that's what they're looking for is actual objects with a camera that are moving. Some of these objects that we see out in the Kuiper Belt, for example, are really small. They take up like 1 pixel, but they're still there and we can see them on camera. So we don't usually see extrasolar planets. We can't
directly image them. We can't take pictures of them because compared to the star that they're going around, they're not very bright. So what we do instead is we use indirect methods, non-picture methods to find them. So the radial velocity method is a very, very common method of detecting extrasolar planets. And what that does, it's also called the wobble method. Sometimes they'll say it called the wobble method, or if you hear anything about a wobble, it's probably the radial velocity method. So what happens with gravity, the reason that we're orbiting around the sun is because we are caught in the sun's gravity, right? We want to rotate around the sun. However, if you remember, gravity is one of those things that it's kind of a two-way street. Everything exerts a force, a gravitational force on everything else. So if we have the sun, we'll call it the primary body, and we have Jupiter, we'll call it the secondary body. That mass is going to be pulling on the sun. The sun is much, much bigger than Jupiter, right? Way, way bigger. However, it's still going to start to kind of wobble because Jupiter is pulling on it. As Jupiter goes around, the star is actually shifting around. So that's what's happening with the Jupiter Sun system. So you have a big enough object, a star, and a big enough body, say Jupiter, pulling on that primary body, you're going to get a wobble. And that's what's going to happen. You're going to have this wobbling effect. Now that we've covered that, what happens with that wobble is if a star, let's say we're here on Earth, we see a star way out there, and the star is wobbling. Well, how can we detect that wobble? We can do it with something called spectroscopy and the Doppler shift. So if you don't know what these things are, that's okay. All you really need to know is that when an object is moving towards us, the light that we're getting is different. We can spectroscopically, we can take that light apart, look at it and go, yeah, this light is different than light as something is traveling away from us. Now, this isn't really a property of nearness and farness. What this is a property of is moving towards us or moving away from us. So there has to actually be movement for us to detect the difference in that light, that shift in the light. But if something is wobbling, we can see this very regular, very periodic, the light gets squished, the light gets lengthened out. Light gets squished, light gets lengthened out. So we can see something coming towards us and away from us, towards us and away from us. And even if that difference is very, very small on an astronomical level, and this object, this star, is very far away from us, we can conclude that there is something pulling on that star, something that we don't see. Now, depending on how much that thing is pulling on the star, we can pretty much determine the mass of the thing, right? If we see that the star has a really large wobble, well, there's probably a really big planet going around this star. Now, of course, things are much, much hairier in real life. That's an oversimplified version. The distance between a large body and a much larger star does matter. But this is the indirect method, the radial velocity method of finding stars based on their wobbling.
So let's move on. We'll be covering this technique and the other techniques too in more detail and using real life data so that we can learn the technique thoroughly in the exoplanet detection modules. So you can refer from there. Moving forward, obviously, being an indirect method, it comes up with some limitations. So here they are. It can only measure movement along the line of sight. Planets that have highly inclined orbits produce smaller visible wobbles and are therefore harder to detect. Third, the Doppler spectroscopy, which is also called the radial velocity meter, is not much useful and trustworthy in case of multi-planet or multi-star systems. Uh, so this was all about radial velocity method. Now handing over to Yashasvi.
So, next method we have is of transits. So, One of the examples which we saw was of Austral B. So this exoplanet was detected by the method of transits, and most known exoplanets have been discovered using this method. In simple words, a transit occurs when a planet passes between a star and its observer. So how does this look like? So in this image on the right, you can see how a transit may seem. There needs to be a specific orientation of the planetary system in order for us to observe the transit. So it should be like there is star and an observer, and the planet is coming in between us. So the orbit needs to be edge on rather than face on, and that is when we will observe the transit. And as the planet it moves between the star and us, we see that the brightness from the star dims. We take the brightness of measure the brightness of the star, and we observe that the brightness of the star dims as the planet moves across it. So a bit theory about it is, the principle is that we observe the dimming of the star's light in the form of light curves. When the planet appears to move across the face of the star, viewed from a particular point which is edge on by us. So as this transiting body, it passes in front of the star, we observe a drop in the brightness of flux which received from the star due to that hindrance caused by the planet, and we see this in the form of transit light curves. So given a suitable alignment, we can see that the light from the host star is it varies because of the transit of planet across its face, and this effect is repeating at the orbital period as the planet revolves around the star. So at an orbital period we can observe this phenomenon. So now to better understand about this, we have a simulation over here. So you can see here that we have a planetary system. So as the planet revolves around the star, we see there is a drop in the brightness. There is a drop in the light curve. So understanding this drop, we can predict whether it is an exoplanet and what the mass of the exoplanet could be, and various other parameters like so. You will understand what all parameters can be determined in the module. So as for this site, there are a lot of options. There are some presets. So we have some preset options which will provide with some specific mass for the star or for the planet. And we also have some presets for actual exoplanets, like where we have for SG209458b. We can check the light curve like this. There are also some other parameters which we can set according to how we want it to look like. So we can set the planet properties or the star properties. We can set the noise for, like over here it is preset to 0.1, but we can change that and so on. So like this we can change all the properties, and then we can find the one which will be most suitable to our observations. So this is a very oversimplified simulation, but it provides a basic understanding of how transits can be observed. This is also provided in the module, so you can check this for yourself as well. You can check for you can shift different parameters and check how it is affecting the light curve. Like for example, how the mass of the planet, or how the mass of the star, or how the size of the star it affects the light curve. So you can check all of these yourself as well. So moving ahead. So like any other detection technique, transits also comes with its own set of limitations. So these limitations can be divided into two groups. One is limitations from the ground, other is limitations from space. So the limitations from ground can be seen like, now for observing transit from ground, we make use of a telescope. So these telescopes have large apertures and we can observe nearby stars from it. But nearby stars are comparatively quite bright, and the telescope apertures are quite large. So the photon noise, which is quite negligible. Thus, photon noise is not a limitation any longer. So limitations on the transit depth or the light curve are rather caused by by other means like atmospheric transparency variations, atmospheric scintillation noise, and detector granularity. So you can understand more about them, but it is basically because of the Earth's atmosphere. Like the atmosphere it is not uniform, right? We have layers. So because of that atmospheric or that gradation, the limitations are caused. Then next we have limitations from space. So limitations from space are mostly because of the stellar surface. They are caused by the star. So on stellar surface, we observe star spots, plages, granulation, or non-radial oscillations, which can be a means for limitations. And another limitation, which is in general common to transit, is that we need a precise alignment of the planet's orbit to observe the transit. Like already shown, we need it to be, the planetary system needs to be edge on for us to be able to view the transit occurring. So like this, we come to the end of this session. I really thank you all for being with us till now. It is quite late still. I'm really glad that many of you are still here. So really, really thank you for that. Now, if you guys have any doubts, please feel free to ask. We are here for some while.